Alright, so this podcast has to do with thermochemistry stoichiometry. And stoichiometry, if you remember, is simply using mole ratios to determine how many products or reactants we make or form or something like that. So anyways, the real difference between just regular stoichiometry and thermostoichiometry is that we have an equation written, alright, and it's balanced. We have 2 waters for every 2 hydrogens for every 1 oxygen. But at the end of this equation, we have a delta H value, alright? And this tells us either the energy absorbed or released when this reaction reacts, alright? So the first thing we might notice is, and this would be a good question, is this exothermic or endothermic? And we know this is endothermic. How come? Because delta H is positive, alright? If delta H is positive, energy is being absorbed. If delta H is negative, energy is being released or lost, and that would be exothermic. So this is an endothermic reaction, which means we are absorbing energy, okay? The next thing is simply, if we look at this first question, there's 2 examples. How much energy would be absorbed if 1.2 kilograms of water were reacted? Alright? So the first thing we need to do is we need to change kilograms into grams. So this is simply 1,200 grams, because there's 1 kilogram equals 1,000 grams. So, anytime we use fence and rail stoichiometry, we start with what we know. So we know 1,200 grams of water. Alright, and because we have balanced equation, we need to get moles, alright? So we're going to use grams of water. We want to convert this into moles of water. And simply that conversion is looking on the periodic table, and for every mole of water, it weighs 18.015 grams. Okay? Alright, so here is where it gets a little bit different. Typically in stoichiometry we have a mole-to-mole ratio that comes next, but we don't want a mole-to-mole ratio because we want to know how much energy. Alright? So this is what we want to end up with. So we want to have this in the top right, 483.6 kilojoules. Alright? But we want to have moles of water in the bottom right as well. Alright? So this much energy is related to these 3 mole ratios. So because there's a 2 in front of water, for every 2 moles of water, 483.6 kilojoules are released. So simply, we're going to multiply across the top, multiply across the bottom, and get our answer. So we're going to have 58,320 kilojoules, all divided by 36.030. Alright? And moles of water is gone, grams of water is gone, so we're left with kilojoules, which is the unit we want. So when we simplify this, we're going to get 16,160 kilojoules. I'm sorry, kilojoules. And then when we round that to significant figures, we're just going to have 16,000 kilojoules. Alright? And that's the amount of energy released, which is why it's a positive value. Alright? The next thing we're going to do is, if 26,345 joules of energy are absorbed, how many grams of hydrogen are produced? So this time we're starting with the energy instead of with a mass. So again, start with what we know, 26,345 joules. And let's see, we're going to go from there to the bottom. So we want joules on the bottom. But notice we know kilojoules. So we need to change those kilojoules into joules. When we do that, we're going to get 483,600 joules. Alright? And that much energy is related to how many moles of hydrogen? It's related to 2 moles of hydrogen. Why is it 2? Because there's a 2 in front of hydrogen in our balanced equation. Alright? We don't want moles of hydrogen, we want grams of hydrogen. So for every 1 mole of hydrogen, the mass of that is 2.0158. Right? And once again, we're going to multiply across the top, and multiply across the bottom, and simplify. So we have 106,212 grams divided by 486,600. Right? And again, moles are gone, joules are gone. and we're left with grams. Alright, so simply, all we're going to do is simplify that. 0.21961 grams. Alright? And probably because we start with 5 sig figs, we'll end with 5 sig figs. Our molar mass for hydrogen has 5, so that is our final answer. Alright, and that is stoichiometry with thermochemistry. You'll have a balanced equation, and at the end of the balanced equation you'll have some kind of delta H value, and that's how you go from joules or kilojoules into moles, using the kilojoules and that delta H in your balanced equation, those coefficients for your balanced